You ever stop and wonder what's really going on when you cook a meal? Or when an old nail starts to rust? I mean, these are just transformations, right? Well, today, we're going to crack the code behind all of it. We're going to dive into the chemistry of change that's happening literally all around us, every single second. So, let's start by looking for some clues.
All right, let's kick things off with a little mystery. What could possibly connect a carton of milk going sour, that bright orange rust you see on an old nail, and just, cooking your dinner? On the surface, they seem completely different, right? But believe it or not, they all share a deep, fundamental secret. And that's it. They're all telling a secret story, a chemical story. So for the next few minutes, let's think of ourselves as chemical detectives. Our mission? To learn how to read the clues and crack the code of this hidden language of change.
Okay, so first things first. As any good detective knows, you've got to know when a crime, or in our case, a chemical event, has even happened. We need to learn how to spot the evidence. The telltale clues that a reaction has gone down.
So clue number 1 is a change in state. What does that mean? Well, it's when something changes its physical form. Like, imagine you mix two clear liquids together and bam, a solid suddenly appears out of nowhere. That is a huge hint that a brand new substance has just been created.
All right, clue number 2. A change in color. And look, I'm not just talking about mixing blue and yellow paint to make green. We all know that one. I'm talking about something more surprising, like when you mix two totally clear liquids and suddenly they turn this deep, vibrant, unexpected color. Now that is a classic sign that a new substance has just been formed.
Our third clue can often be the most dramatic one of all, the evolution of a gas. Seriously, if you see bubbles, fizzing, or even smoke coming from somewhere it shouldn't be, you are almost certainly watching a chemical reaction happen in real time.
Want a perfect example? Just take a piece of zinc metal and drop it into some acid. You see all those bubbles fizzing up like crazy? That's hydrogen gas being created right there, right before your eyes. It's a clear, unmistakable chemical change.
And our final clue is a change in temperature. Sometimes a reaction kicks out a bunch of energy, and the container it's in will get noticeably hot. Other times, it's the opposite. It'll suck in energy, making everything around it feel surprisingly cold. Either way, that shift in energy, it's a dead giveaway.
Okay, so now we know how to spot a reaction. That's awesome. But how do we actually talk about it? How do we describe it? Scientists needed a clear, universal way to write down what was happening. Basically, they had to invent a kind of secret language. Let's take a look at how that language came to be.
At first, they just wrote it out, like a regular sentence. And yeah, it gets the point across, sure. But it's also really long, kind of clunky, and just not very efficient if you're trying to do actual science. There had to be a better way, right?
And of course there was. The word equation was a huge improvement. It neatly separates the ingredients, what we call the reactants, on the left side, from the final result, the product, on the right. And that simple little arrow in the middle, that just shows the direction of the change. So much clearer, way better.
But this is the real deal, the chemical equation. See, by using symbols for the elements, we get this amazing shorthand that any chemist anywhere on the planet can look at and understand instantly. It's short, it's packed with information. This is the true secret language of chemistry.
Now, this secret language isn't just about grammar. It has one single, unbreakable rule, a fundamental law that governs every chemical reaction that has ever happened or ever will happen. And trust me, understanding this rule is the key to all of it.
And here it is, the law of conservation of mass. Put simply, it just means you can't create matter out of nothing, and you can't make it vanish into thin air. Whatever you start with has to be there at the end. It's all got to be accounted for. No exceptions. Ever.
So what does this mean for our chemical equations? It means the number of atoms for each element has to be exactly the same on both sides of that arrow. If they're not, we call the equation unbalanced. And an unbalanced equation is basically telling a story that's physically impossible in our universe.
And this brings us to a really fun and honestly super satisfying skill, balancing equations. The best way to think about it is like a logic puzzle. We're not changing what happens in the reaction, we're just doing the accounting, making sure all the atoms add up so that our story follows that one unbreakable rule of the universe. Okay, let's try to solve one of these puzzles together. Look at this equation. It's clearly unbalanced. The atoms just don't match on both sides. It's a bit of a mess.
So a good strategy is usually to start with the most complicated-looking part, which here is that iron oxide, Fe3O4. You see it has 4 oxygen atoms, right? So to match that, we need to put a big 4 in front of the H2O on the left side. Okay, step 1 is done.
All right, well, that move fixed our oxygen problem, but it created a new one. Now we have 8 hydrogen atoms on the left, since 4 times 2 is 8, but we only have 2 on the right. No big deal. We can fix that easily. We just put a 4 in front of the H2 on the right side, and just like that, our hydrogens are all balanced out.
We are so close. The only thing left to tackle is the iron. We've got 3 iron atoms on the right, so you guessed it, we just need to stick a 3 in front of the Fe on the left. And now for the final check. Let's count them up. 3 iron on each side, 8 hydrogen, 4 oxygen. It's perfect. Puzzle solved.
And there it is, our final, perfectly balanced equation. It's not just a jumble of letters and numbers anymore, is it? This is a complete, accurate story. It's the story of a chemical transformation, told in a language that lines up perfectly with the laws of the universe.
So now that we can read and write this language, we can start to notice something cool. We can see that different reactions tend to follow certain patterns, almost like genres in a bookstore. You've got your mysteries, your romances. Well, in chemistry, we have genres too. Let's explore a couple of the big ones.
First up, we have the combination reaction. This is probably the simplest story you can tell in chemistry. 2 or more things come together to form one single, more complex thing. Think of it as an A plus B makes AB kind of story. It's all about coming together.
A fantastic example of this is when you add water to something called quicklime. The calcium oxide and the water combine to make just one new thing, calcium hydroxide. But what's really cool is that this reaction releases a ton of heat. You can literally feel the container get hot in your hand. That's a classic sign of what we call an exothermic reaction. It's a reaction that gives off energy.
And then you have the total opposite, the decomposition reaction. If combination was a coming together story, this is a breaking apart story. You start with one complex thing, and it breaks down into 2 or more simpler things. Your AB becomes A and B.
A perfect example? Take these green ferrous sulfate crystals. When you heat them up, that one single compound just breaks apart. It decomposes into 3 totally separate, simpler substances. You get a solid and 2 different kinds of gas. So one thing becomes 3. That's decomposition in a nutshell.
So why does any of this matter? I mean, really, why should you care? Because this secret language, it describes the most important stories in the universe. In fact, this equation right here is the story of you, right now. It's respiration. It's the chemical story of how the sugar from your food combines with the oxygen you're breathing to make the carbon dioxide you're exhaling, the water that's in your body, and, this is the big one, the energy that is keeping you alive this very second. This isn't just about chemistry in a lab. This is about life itself.
So there you have it. You now have the basic tools to be a chemical detective. You know how to spot the clues, you can read the secret language, and you can understand the basic plots. So the only real question left is, as you go about the rest of your day, what other secret chemical stories are you going to notice unfolding all around you?